So what is the Biot-Savart law? So uh remember we learned last time if I want to find the magnetic field B, then I know that B equals to, mu zero divided by 4 pi, and then integral of, if I have a charge that's moving in space, it's QV crosses R cap and divided by the R squared. And then yeah, dr. Okay. And then it's also equal to the mu zero divided by 4 pi and then times the integral of I dl, and then dl is a vector that points in the direction of the current and then crosses the r cap vector and then divided by r squared. Okay, so if we want to write the magnetic field here, right? So okay, if I look at this infinitesimal segment of the wire has length dl, and this will be the dl vector. So dl be in that direction. Now, what's my r cap direction? Well, my r vector would point from this infinitesimal segment to the point P. So r cap will look something like that. Okay, if I do the cross product between the two, use your right hand rule, right? So I have my fingers point in the direction of DL, so maybe that way. And then I curl my fingers in the direction to the point P, so it'll be looking like that. And if I do the cross product, it'll be pointing in something like that, or okay, probably be in around that direction. Now notice that once I do this entire integral, I'm actually integrating a bunch of vectors because when I do dl crosses the r cap, I'm getting a vector. And once I do the integral of all the vectors, you'll see that the horizontal components of the magnetic of each magnetic field contribution, the horizontal components will all cancel out, and what's left is a vertical component. So the final magnetic field will be pointing upwards. And it makes sense because if you use your right hand rule to find the direction of the magnetic field, like you curl your fingers this way, you'll find that the magnetic field at any height above the center of the wire will always be pointing upwards. So if I want to do a scalar integral, then I'd have to project the dl crosses r onto the vertical direction. So okay, dl crosses the r. The magnitude of this is dl times r because dl is indeed perpendicular, always perpendicular to your r vector. So dl times the magnitude of r cap, which is just one, right? So dl. Uh, but I have that the dl crosses r has two components, right? A vertical component and a horizontal component, or like radial component. And I only want the vertical component over here. And so how do I find that? Well, notice that we have two similar triangles. So uh I have one triangle that looks like this. It's a right triangle, by the way. And I have another triangle like that. And those two triangles are similar. If I want to project onto the vertical direction, that angle for here, I'll let that be theta. I also know that it's equal to this angle here over here, theta, right? And if I want to project onto the vertical direction, I'll do dl times the sine of the theta, right? Now what's sine theta? Well, sine theta is just r divided by square root of r squared plus h squared, right? So then I'll be getting equals to dl times r over square root of r squared plus h squared. Now I'll plug that into my integral over here. Notice that I'll be getting, let's see, let me draw a divider. Uh, okay. So I want the magnetic field. So B would equal to mu 0 divided by 4 pi. And inside my integral, notice that I is constant over this entire wire, so I can pull it out of the integral. Also, dl sine theta, like dl crosses r cap, right? That's dl sine theta. That's always constant. So it will be mu 0 I over 4 pi, and then uh wait, integral of dl times r divided by square root of r squared plus h squared. Now, what is this r squared term over here? Okay, maybe I should write r prime. Was r squared over here or r prime squared over here, right? Don't get this confused with the radius of the circular ring because it's actually supposed to be the distance from the point under investigation to the point on the wire. And notice that r prime squared is not the radius of the wire squared. It's going to be r squared plus h squared because we're looking we're looking at this distance over here, not the radius of the wire. So on the denominator, we'll be getting another, so getting r squared plus h squared. And now once we do the integral, notice that integral of dl is just 2 pi r. It's just the circumference of the wire. And the r over like r squared plus h squared to the 3/2 power, that's always constant. So if I want to actually do the integral, it will just be mu 0 I times h, or sorry, oh, my bad. Okay, times 2 pi r, and then times another r, right? So 2 pi r squared divided by 4 pi times r squared plus h squared to the 3/2 power. And you'll find that the 2 pi and 4 pi cancel to just make a 2. So this will be your final answer. Mu 0 I, um, there's another r here. Mu 0 I times r divided by 2 r squared plus h squared to the 3/2 power. Yeah, that was just an application of Biot-Savart law. Make sure you're familiar with Biot-Savart law, and you should be good. Okay, let's move on. Show that the magnetic force can never do any work by considering the work done on a charged particle moving in a magnetic field with the work integral. Okay, remember, the magnetic force is Q, V crosses the B. Now, what is work? Definition of work is I have integral over some over the path of some like particle, right? And it will be the force on the particle times infinitesimal, or the dot product between the force vector and the infinitesimal length segment on which the particle is moving on. So it'll be the integral of the f vector dot to ds vector. Well, what is this ds vector? I can also write it as f integral of f dot onto the ds vector and then divided by dt and then times dt again. I mean, that's just multiplication because the two dt's cancel, right? Well, what is ds over dt? This is just the velocity vector. So my work is also equal to the integral of the force vector dotted onto the velocity vector and then integrate over dt. Okay, well, what's our force here? Our force is qv crosses b. Well, what's the definition of cross product, right? So if I do v crosses the b, then I'll get a vector that's perpendicular to both v and b. So if I plug this in for f, notice that I'm dotting that onto the v vector itself. So what I'm doing is I'm taking a vector that's perpendicular to the velocity vector, and I look at the dot product with the velocity vector itself. Well, what does that give you? Remember, the dot product gives us like the dot product is 0 if I dot two perpendicular vectors together. And here I have the force vector is always perpendicular to the velocity vector. So the work done is always equal to 0 because this integral, inside the integral, it will always be 0. Okay, so Yeah, that's just another application of mechanics and what we learned about the magnetic force last class. Let's move on. Okay, a semicircle wire is given by the equation x equals square root r squared minus y squared, where r is a constant. There's a constant current I generated through the wire that travels from the left end to the right end. Given that there is a uniform magnetic field of strength B pointing out of the page, find the net force on the wire. Okay, I'll just quickly go over the gist of the problem, but I won't go into the specific calculational details because um, it's pretty similar to the first problem we did. Let me set up my coordinate axis. Um, okay, so this will be my x direction, this will be my y direction, and this will be my z direction. So this is the equation of my semicircular wire. So looks something like this. That'll be my semicircular wire, and this distance over here is r. Okay, now there's a constant current I generated through the wire that travels from left through the right end. So that's my current I. Remember that this semicircular wire is in the in the XY plane. Uh, but there's a uniform magnetic field pointing out of the page, so it's pointing in the negative Y direction. So B would equal to the magnitude of B, which is uniform everywhere, and in the negative Y cap direction. So because I was pointing out of the screen, so it's in the negative Y cap direction. Okay, find the net force on the wire. Well, how you do this is just, that again, another form of the magnetic force is the total force is I'll do an integral of the current and then I'll do the dl vector cross product with the magnetic field vector. Well, when you're doing this, just keep in mind that when you do the cross product, you're getting a vector. So for example, I'll just illustrate here. Uh, we're looking at the right. Okay, so this will be, for example, if I look here, right? My DL vector will be pointing this direction. My B vector will be pointing in this direction. So when you do the cross product, sorry, I'll do another color to make it more clear. There we go. So when we do that, you have to keep in mind there's an angle between the two vectors. So when you do the cross product, you have to keep in mind that you need to take the perpendicular components of the two vectors, and that will be changing as you go across the wire because the direction of your DL will be changing, but the direction of the B will not be changing. Yeah, so just you can just work out the integral, and after you integrate, you'll find the net force on the wire. That should be solvable on your own, and if you guys really want me to do this, I can go over this. You can like send me an email and I can go over it next class. Yeah. All right. This problem is just the same as the first problem we did, so we can skip over this. And the magnitude of net magnetic field at point P. Well, for this problem, notice that I have two of the wire loops. If I want to draw the magnetic field, well, at the point P over here, if I just look at the magnetic field due to the top wire, well, we know that if we have a wire loop, use the right-hand rule, you can find that like this will be the direction of the magnetic field, or like this is what the magnetic field lines look like. You look like that. This direction of field lines. So if I'm looking at a point P over here, then the direction of the magnetic field due to the top wire would be looking like this. So it'll be pointing upwards towards the center of the top wire. Now, if I have another wire, except it's on the bottom, so it's over here, well, the same thing. Like if I draw the magnetic field lines, it again looks like that. And I have like few lines that look like that. So if I'm looking at the point P again, then the contribution of a magnetic field due to the bottom one, the bottom wire loop would be that way. So the total magnetic field is just I add the two magnetic field contributions together. So it'll just be 2 times the B of each individual wire. And to find the B of the individual wire, well, we did that in the first homework problem. So yeah, that will be the answer for the magnetic field at the point P. Uh, yeah. So just to remember the direction, like what the magnetic field lines look like around each wire loop, and remember the superposition principle, which is just you have many sources of magnetic field, then the magnetic field at a certain point is just you add the magnetic fields of each source together, and you'll get the total magnetic field. Yeah. All right, let's go on to the lesson today. It's on Ampere's and Faraday's law. So last class we went over Biot-Savart law, and we also went over the magnetic force, or like also known as like the Lorentz force. So this time we're gonna look at the Ampere's and Faraday's law, which it's more advanced topics in magnetism, and you'll see they'll be really important, and they'll help you solve a lot of problems. So first, Ampere law. Okay, so Ampere's law, why do we use it? Okay, so Ampere's law, it's equivalent to Biot-Savart law, but in some cases, or I should say in a lot of cases, um, using Biot-Savart law, yes, you might get the correct, you'll definitely get the correct answer, but if you apply Ampere's law, it will be so much easier to get to the right answer because using Biot-Savart law, you have an integral of like, for example, q v and then crosses your r cap divided by the r squared, right? And then like mu zero divided by 4 pi on the outside, and that equals to your b. Well, a tricky point is that v crosses the r. That's both of them are vectors, right? And I'm doing a cross product. So the result of that is I'm integrating a vector, and that can be pretty tricky because you have to take into account the direction of each v crosses r vector. Um, and similarly, you have the one where you integrate the I dl crosses the r cap divided by r squared. You know that, right? So integrating a vector can be tricky, and also a lot of the times it's just hard to do this integral. Now, Ampere's law, you'll find that in many cases, it will be much easier to do. First thing is that when you do the B dot to DL, it's a dot product between two vectors. So remember, if I have two vectors and do a dot product, I get a scalar. And that's really nice because once I get a scalar, then I don't really need to worry about the direction of like each thing I'm integrating because it's a scalar. It's just a quantity. It has no direction that I need to consider. And you'll find in many cases that, for example, if I'm looking at the field due to a conducting wire, an infinite conducting wire, it will be so much easier to use the Ampere's law than to use Biot-Savart law to find the magnetic field outside of the wire. So think back to electric fields. Uh, Originally, we could sum up all of the DE contributions, or if there's symmetry, we can use Gauss's law. Now, in magnetism, think of summing up all the DE contributions. In magnetism, it's the dB contributions. Now, basically just infinitesimal magnetic field contributions. That you can think of as the Biot-Savart law way. If there's some certain symmetry in electric field case, we could use Gauss's law. Now, Ampere's law is sort of like if we have a nice scenario, we could apply Ampere's law, and it will be so much easier than summing up each of the dB contributions or like doing the Biot-Savart law integral. So let's look at an example. Or actually, first, you need to know what Ampere's law is, right? So Ampere's law says that, if I have a path integral of B, the magnetic field vector dot onto the DL vector. So just an infinitesimal segment. What does this mean? Well, notice that like in the integral, I wrote a circle on the integral. What does that mean? Well, that represents what's called a path integral. So a path integral is like, so first, what's a path, right? So I have a starting location in space, and then your path, it can be like just any path as long as as long as it ends back at the starting location. So it has to be a closed path. Now, what so what's the path integral, right? So the path integral is just I do the integral of b dot to dl on all points along this path, and I just like I take the b dot to dl on every point along the path, and then I sum it all together because that's what an integral is. So essentially, I'm just integrating over a certain closed path. Now, Biot-Savart law tells us that this integral of path integral of b dot to dl that equals to mu zero times the current on that path. And you can see it's like a pretty simple formula, right? And you'll find that it really simplifies a lot of cases and really helps us like uh in certain situations, it'll be much easier to use Ampere's law than to use the Biot-Savart law. Let me give an example. So we're looking here at we have a conducting wire and we want to find the magnetic field a distance away from the wire. And one thing to emphasize is that this conducting wire, it has to be infinitely long. Why? Well, okay, so if I have an infinitely long wire, then I'm able to say, with the right hand rule, I know that this is what the magnetic field lines look like, right? So it's a bunch of concentric circles that it's like a bunch of them stacked on top of each other. So like you can look at this diagram over here. Now, if it's infinite, you can imagine that there's like a certain symmetry, right? Because if it's infinitely long, then like um a point on the wire over here, if I'm looking at like the magnetic field over here, right? And it's at some distance like d away from the wire. And then I'm looking at a point over here and it's also a distance d away from the wire, but it's like, some height below, like it's some height below the first point, right? Now, if it's infinitely long, then of course I know that h is much less than the length of the wire. So I can just say that the magnetic field at these 2 points, they're equivalent, right? Because it's infinitely long. Like this finite distance, it's so small compared to the infinite length of the wire that we can just say these 2 points are the same, right? They have the same magnetic field. The problem is that if we have a finite wire, so this is my this will be my finite wire, it has finite length, then we can no longer say that the magnetic field over here is the same as the magnetic field over there, even though they're the same distance away from the wire. You can use Biot-Savart law to find that the magnetic field at these 2 points, it's not the same. So it's really difficult to deal with these finite wire situations. And if you have an infinite wire instead, it's like it simplifies the problem a lot and like it adds symmetry to the problem, which is like much easier. So let's go back to I want to find the magnetic field due to an infinite conducting wire. So this is my infinite wire. And I'll demonstrate why Biot-Savart law is like it will be hard to use if I want to, it will be hard to find a magnetic field if I want to use Biot-Savart law. So for example, remember Biot-Savart law, I have B equals to the mu zero over 4 pi, and then I integrate I times dl, the dl vector, crosses the r cat vector, and then divided by the r squared. Okay, so all right, so I'm looking at a point P over here, which is like a distance, let's say it's a distance d away, perpendicular distance d away from the wire. Now I'm gonna do this integral, right? First off, dl crosses r, that's a vector. And um, actually, okay, yeah, so let's just do it. So this is my dl vector, dl, and then this will be my r cat vector. If I do the cross product, right, you'll find that it will be pointing out of the screen. So it will be pointing in uh this direction. So out of the screen. But the problem is that when I'm doing the cross product between DL and R cap, I have to, if I want to find the magnitude of it, okay, I need to project the r cap direction onto this direction because when I'm doing the cross product, I need two perpendicular vectors, right? The horizontal component of the r cap vector, so this component, when I do the cross product with the DL vector, it will be zero because they're parallel. So the only component of the r cap vector that'll like after I cross product it with the DL vector that'll like be non-zero be this component. I actually want the magnitude of the DL crosses the R, I need to multiply the magnitudes of these two vectors. And this vector over here is only a component of the r cap vector. And the problem is that if I look at like a segment over here, now my r cap is pointing that way and my DL is pointing this way. And you can see that r cap, it's at a different angle with the horizontal, meaning that the perpendicular component to the DL vector that has changed. So everywhere along the wire, the DL crosses the R, that's not going to be constant. So it'll be like you have to do some geometry and stuff, and you'll not get you'll be able to do the integral, but it's not the easiest way to solve the problem. You can really see that like it's starting to get a bit tricky to find the magnetic field like at a distance from an infinite wire. Now, instead, if we use Ampere's law, which says this, right? Integral B dot dl path integral equals to mu zero I. Well, if this is my wire and I want to find the magnetic field at like, distance d away from the wire, so this is d. Well, I know that the magnetic field, it runs in circles, right? Uh, actually, let me go to a different screen so that it has a better diagram. Yeah, this one. Okay, so you can see this is the top view of the infinite wire. Now the magnetic field, it runs in circles, right? Um, if I want to find a magnetic field, like for example, distance d away over here, because there is symmetry, I know that along this circle over here, along that circle, the magnetic field is constant. It always points like the magnitude of the magnetic field is always constant, and the magnetic field always points tangentially to the circle. So for example, if I look over here, the magnetic field will be pointing in this direction. If I go over here, the magnetic field will be pointing in that direction, and their magnitudes are equal. So if I use the Ampere's law, B dot onto DL, B dot onto DL, and I choose my closed loop path to just be this. Shoot, let me redraw my closed loop path. That'll be my path. It's just a circle. Now, everywhere along that path, d dot to dl is constant because dl always points in the direction of b. So then the result of the integral is just b times the integral of dl, closed loop. And what is the closed loop integral of dl? Well, that's just the circumference of the circle. So I'm just getting 2 pi r times b. And that equals to mu zero and then times the enclosed current. The enclosed current will be the current I, which will be mu zero I. So I'm just getting it's just really simple. I get B as a function of R or D, whatever, it doesn't matter. So as a function of distance from the wire, it will be mu zero I divided by 2 pi times D. That's just our expression for magnetic field. And you can see this is just like, it's just one line and you can find the magnetic field, the distance from an infinite long wire. And like, you don't have to do a really nasty integral using Biot-Savart law. So you can see that in some cases, using Ampere's law can be much, much simpler than having to do the Biot-Savart law. Okay, let's go on to this problem over here. So using Ampere's law, can we find the magnetic field distance from r away from an infinitely long wire carrying a current, the magnetic field at a distance r away from a finite wire carrying current, the magnetic field at the center of a loop of current, and the magnetic field between two infinitely long wires carrying currents. I'll give you guys a moment to think about this. If you're watching the recording, just pause the recording and think about it for a few minutes. Okay, we're back. All right, let's first look at the first one, the magnetic field at distance r away from an infinitely long wire carrying current. Of course, we can do this. We just did it like we did it just now. Like we found the magnetic field from an infinitely long wire carrying a current. So this is true. So yes. Magnetic field distance r away from a finite wire carrying a current. No, we cannot do this because if we have a finite wire, we can no longer say that like 2 points along the wire are equivalent. So everywhere along the wire, it will have different magnetic fields, and you'll find that the magnetic field lines will look pretty complicated, especially at like, when the wire ends. Like if you use Biot-Savart law, you'll find that the magnetic field lines it wouldn't be looking like just like simple concentric circles. So that's the tricky point of you having a finite wire that we talked about that a few minutes ago, right? If you want to find a magnetic field at a distance r away from a finite wire that contains current, you cannot use the Ampere law anymore. You have to use Biot-Savart law. Magnetic field at the center of a loop of current. So let's wait. Then, all right, center of a loop of current. Well, that's also a bit tricky. So at the center of a loop of current, the magnetic field will be pointing upwards if my current is moving in this direction, because you do your right hand rule, my current curls in that way, so my magnetic field will be pointing upwards. Well, so if I want to use Ampere's law, remember it requires doing a path integral of B dot onto dl. And when we applied it to the case of doing and like we applied it to the case of finding the magnetic field from infinitely long wire, right? We were able to do that because magnetic field runs in circles. So if I choose the convenient path that looks like this along like one circle, everywhere along the circle, the B field is constant. Now, if I want to do the path integral, I need a non-zero path. Problem is, when I want to do it, like if I try to find a magnetic field at the center of a loop of current, I want to use Ampere law. We can't do that because if I want to find a path where the magnetic field is always equal, like it's equal everywhere, otherwise it'll be a complicated path, right? It doesn't simplify the problem. If I want to find a path that has equal a path where everywhere the magnetic field equals to the magnetic field at the center of a loop of current, well, that's not possible to find a non-zero path because at the center the of the loop of current, that's the only place in space that has that certain magnetic field. Because uh you'll find that like if you want to actually use you want to use Ampere's law, you can't have a non-zero path. So I won't be able to do the Ampere's law because B dot to DL, that'll be a zero path. So like I'll just get zero and then I won't be able to enclose any current because my path will not enclose any of this current loop. That's a problem why in certain cases I cannot use Ampere's law. So in this case, I cannot use Ampere's law to find a magnetic field at the center of a loop of current. To do that, all you can do is use Biot-Savart law. Like DL crosses the R, like this is my R, this is my DL, and you'll find like you integrate a bunch of vectors that point directly upwards. Now, the magnetic field between two infinitely long wires containing current, yes, we can do that because I know the magnetic field due to one infinitely long wire. So then if I add that to the magnetic field due to the other infinitely long wire, then I'll be able to find the magnetic field due to two wires. And I can also have like 3 wires or 100 wires. All I have to do is just add the magnetic field vectors together and I'll get the total magnetic field. So the answer to this problem is yes. Okay, let's move on. Okay, we just did that. Yep. All right. Given an infinitely long, oh yeah, so these are just some examples. Given an infinitely long wire carrying some current, Yash measures a magnetic field. How far away is he from the wire? And also Ryan takes an infinitely long wire, measures a magnetic field, the distance away, how much current is going through the wire. Well, remember, we found that B from an infinitely long wire, it's just mu zero I over 2 pi R. In these two problems, you're given two of the variables, you just solve for the third variable. So just remember this formula, how we got it from the Ampere's law, and just plug in the numbers and solve for the other variable, and you should be good. I trust that all of you guys can do this. Okay, let's go on. All right, each wire in each diagram is infinitely long and has a current of 3 amperes. Calculate the magnetic field at each mark point. I'll give you guys pause the recording and you guys can try this out. Okay, we're back. So, okay, let's look at the first problem. I want to find the magnetic field over there. Well, if I want to use my right-hand rule and I find the direction of the magnetic field due to each wire, well, due to the top wire, I do the right-hand rule. I'll find that the magnetic field will point into the screen. Now, if I do the same thing for this wire over here, then I do my right-hand rule, so my current points downwards, which will be the direction of my thumb, and then I curl my fingers. That will be the direction that my magnetic field curls. And that also has, like the magnetic field at the X point will also be pointing into the screen. And also the same for these two wires. So the total magnetic field at the X point or at the center of the square, that will just be 4 times the magnetic field due to each of the wires, and it will be pointing into the screen. So the B total would equal to 4 times each individual B field, right? So it'll be mu 0 and then times the current, which will be times 3, and then divided by 2 pi r, right? So 2 pi and the distance from the point, so that'll be 3 meters. So 2 pi times 3 meters. So you'll be getting oh shoot, sorry, the current is, oh wait, actually, yeah, we're good. Okay. Yeah, so we'll be getting 2 mu 0 divided by pi. Okay, and second question, calculate the magnetic field of over here. Well, okay, so this is the direction of the currents. If I look at the the magnetic field generated by the top wire, I use the right-hand rule, it'll be pointing into the page over here at the X point, and so is the magnetic field due to this wire over here. Now, the wire over here, if I use the right-hand rule, it will create a magnetic field that points out of the page. And okay, so this will be the magnetic field due to those two wires, but due to this wire over here, will be pointing out of the page. So actually, when you want to find the total magnetic field, you'll be doing the mu 0 and because they each have the same current, right? So mu 0 I divided by 2 pi. And in the parentheses, I'll do 1 over, if I let the positive direction be into the page, well, I know that this distance is 15. So it'll be 1 over 15, and then plus 1 over 5. But then because the magnetic field due to this one is pointing in a negative direction, which is out of the screen, it'll be minus 1 over 5. So your final answer after you plug in I, which is 3, right? You'll be getting 3 mu 0 over, over 30. Oh, shoot. Yeah, over 30 pi. So just mu 0 over 10 pi. And it'll be pointing into the page. So third example, I highly recommend if you want to review last week's class. plus this week's what we learned about the Ampere's law, because it helps you review the direction of the magnetic field due to a wire, and also like applying Ampere's law to finding the magnetic field due to an infinitely long wire. Okay, let's go on to the next problem. Yep. All right, so let's talk about solenoids. So what are solenoids? So solenoids are just you have a wire and you loop it around like a cylinder. And you can think of it as, you have it's like you've seen springs, right? So springs look like this. Solenoids are they just look like springs, except instead of an actual spring, it's a wire, like it's like the spring consists of a wire that loops around. And also we don't look at a compression or a stretching of the spring. So like this, like you can just see the overall shape of a solenoid. It kind of looks like a spring, right? But that's not its function. We don't care about the solenoid stretching or compressing. Like so it's not really a spring, but it looks like a spring and we just run a current through it. Now, uh, we assume that the solenoid is infinitely long. So what that means is just the length of the solenoid is much, much greater than its diameter. Now we separate, yeah, so when we're doing calculating the magnetic field due to a solenoid, we separate it into individual windings. What does that mean? Is like, okay, so this is my original solenoid. So what it looks like. So it's just one wire that loops around. I'll simplify this to just I have a bunch of these wire loops. They all carry the same current and they're all stacked on top of each other. And it's actually equivalent. It's a good approximation, and it will be much easier to find the magnetic field due to the solenoid. Now, uh, the magnetic field is approximately parallel to the central axis inside the solenoid. So inside a solenoid, you can see in this picture over here, the magnetic field, it runs parallel, roughly parallel to the central axis. Okay, let's go on to finding the magnetic field due to the solenoid. All right, so this is a really good application of the Ampere's law. So remember, this is our Ampere's law. So magnetic field B dot onto dl, and we do a closed loop integral. That equals to our mu zero and times the I enclosed. Yeah, be sure that like this I enclosed is just the amount of current that your path encloses. So if I choose this path over here, this rectangular path, I want to do the path integral of B dot to dl. Well, notice that on this segment over here, so uh top segment, there's no magnetic field on the outside because that's one of our assumptions. So the B dot to dl in that segment will be equal to 0. Now on this segment, you can see part of it has 0, part of the path is in a region with 0 magnetic field, and part of it is in a region with a magnetic field. But remember, when we're doing the integral, we're doing path integral of B dot onto the dl. Here, I draw your DL will be pointing downwards, right? Your magnetic field B is pointing to the right. So if I do the dot product between the two vectors, I'm getting 0 because the two vectors are perpendicular. And by the definition of dot product, like perpendicular vectors, their dot product is 0. So uh this segment of the path that will give you 0 when you do the integral, and so will this path because it's also like we have the path is perpendicular to the magnetic field. So the only contribution to the integral would be the bottom part, which is where we have the path that's moving parallel to the magnetic field. And because it's infinitely long, the magnetic field over here, so uh, magnetic field everywhere along this segment of the path will be equal because it's infinitely long. We can make that approximation. So we can say that path integral of B dot to dl, right? B dot to dl, because dl is always it's always parallel to B. This just equals to B and then times the length. So B times, we call it H here. And then that equals to mu zero times the enclosed current I. What is that? That is mu zero times each individual current, so basically the current through the solenoid, and times the number of current loops that this path encloses. So we'll call that big N for now. So then the B would equal to the mu zero I n times big N divided by the H. Now, what is big N divided by H? Well, notice that this is constant no matter, like big N over H, we'll call that small n, which is just the density of the current loop. So it's just the number of current loops, or like the number of turns in your solenoid per unit length, the number of turns per length. And that's constant no matter what path we choose, because small n is just a property intrinsic to the solenoid that you're looking at. So then, okay, we're just getting B equals to mu zero I times n. And you can see how this is like, it's a, like, it's just one line and we got, or two lines, whatever. Like, really simple way to find the magnetic field due to the solenoid. And if you imagine using Biot-Savart law instead, then like I have so many current loops. I first need to do an integral to find the current loop due to each uh I first need to do an integral to find the magnetic field due to each current loop, and I then have to integrate that to find the total magnetic field. Imagine how complicated that can be. And just using the Ampere law is simplified it by so much. So you can start seeing how Ampere's law starts getting really useful when you're solving these problems. All right, let's go to the next part. Faraday's law. Okay. All right, Faraday's law, it's another big theorem that you need to know in magnetism. So what it says is that uh, a change in flux, it creates a voltage. Um, It's also known as Lenz's law. Okay, EMF. Okay, you see EMF here, it just means voltage. Okay, so what is magnetic flux? Well, you might have heard of the word flux before. I might have taught it to you. I don't remember, but let's just go over it again. So imagine I have a magnetic field that points upwards in space. Okay, now if I had a square loop over here, or I had a loop over here, like a current loop over there, or just whatever, some like enclosed area, and it has total area A. The magnetic flux phi, we define it to be equal to the 2D surface integral of B dot onto dA vector. And by the way, the dA vector is, if I have a surface over here, maybe it's a curved surface. The vector over here, for example, the dA vector over here will be a vector that's it represents an infinitesimal area, and it will be the magnitude of the infinitesimal area, which is dA, and then its direction will be perpendicular to the surface. So yeah, that's just the definition of the dA vector. Now, in this case, right, I have the magnetic field. It's always parallel to the dA vector because it's always perpendicular to the surface of it's always perpendicular to the surface, right? So then in this case, my magnetic flux would be equal to B times A. Now imagine if I instead had, for example, I had this was my surface still, it's still horizontal, but this is what my magnetic field looks like. So it's slanted and it makes some angle theta with the horizontal, or yeah, or I'll let this angle be theta with the vertical. Well, then if you do the dot product, you'll find that the flux now equals to, my flux would equal to B times A, except because I need to do the dot product, it will be B times A times cosine of the theta, right? So that's just like definition of magnetic flux. Now, what the Faraday law tells you is that if I have a flux and it's changing over time, that would generate a voltage, or like it's like formerly called an EMF, but you can think of it as voltage. So an example of this would be if I had a current loop. Initially, it has no current, and initially I have, for example, it has zero magnetic field. There's zero magnetic field in the beginning. Now, imagine if I increase the magnetic field over time, so dB over dt, and also oh yeah, dB over dt would not equal to zero. So the magnetic field is changing. And say I fix the area of the current loop. So then I have d phi over dt, because the b is changing, then d phi over dt would not equal to zero. So d phi over dt is non-zero, and it will be equal to negative of the voltage generated. So why negative? You'll start seeing why. So if I have a magnetic field and it's increasing, so this will be increasing, well, then what will happen is that, um, okay, the magnetic field generated by the induced current will have to oppose the change in the magnetic flux. Uh, Let me actually go on to the next slide. Yeah, the induced current runs in such a way that the magnetic field created by the induced current tries to oppose the change in flux. So right now, the flux is increasing, and the direction of the increasing flux will be upwards. So what the induced current would do is that it wants to induce a current such that there will be a magnetic field that will be going downwards because it wants to oppose the change in flux. So what will happen is that there will be a magnetic field that points in this direction. And the reason is because if you use your right hand rule, then if you curl your fingers in the direction of the current, the generated magnetic field will be pointing downwards. And because my magnetic field is like the magnetic field is increasing upwards, or the flux is increasing and the magnetic field points upwards, then I want to generate a magnetic field that points downwards because it opposes change in flux. Okay, let's go on. I'll do some examples so that it becomes more clear. Given a wire on the screen, so magnetic field pointing into the page, determine what direction the current will flow in the following examples. Okay, so let me draw it first before you guys do it. So this is my wire loop. Now, wire loop, by the way, it needs to be a closed loop. Otherwise, you can't have a current, right? This is my wire loop. And then I have a magnetic field that points into the page. Okay. This will be my magnetic field. Something like that. And it's uniform in all space. All right. So right now, okay, even if okay, you have a magnetic field, right? So there's a certain flux, but that doesn't mean that there will be EMF induced. Because the reason is Faraday's law gives us that epsilon equals to negative d phi, which is the flux, right? Over dt. There'll only be an epsilon induced EMF if my flux is changing over time. Uh, in a stationary case, that there's no change in the flux, so there will be no EMF induced. Only when like the flux is changing, then I have an EMF induced. So for example, when the magnetic field is increasing, okay, what would happen? Well, right now the magnetic field points into the page. So you can think of like the flux, if it had a direction, will be pointing into the page. Because the B, if I do like B times the area, right? It'll be pointing into the page. Now, if the magnetic field is increasing, then the flux is increasing into the page. The induced current will be in such a way such that it opposes this change in the flux. So that's why we have a negative here, right? And so if I had a current that ran uh, counterclockwise, so this way, what it will do is because of this current, there will be a magnetic field generated that points out of the screen instead of into the screen. So we're pointing this way, right? If you use your right hand rule, and that'll oppose the increase of flux into the page. And that's why the induced current will be pointing counterclockwise and not clockwise. Now, if the loop of wire instead shrinks in size, let's look at what will happen, right? So loop of wire shrinks in size. Remember, we have phi equals to B times the A. Well, if the loop of wire shrinks in size, then your A is decreasing. So d phi over dt is negative. And so the change in flux is uh, because the flux was into the page, but now it's decreasing. You can think of the change in flux as pointing out of the page. And because the change in flux is pointing out of the page, a current needs to be induced so that there will be a magnetic field pointing into the page. And how does that happen? Well, that will happen if I have a current moving clockwise, because this way, you do a right-hand rule, the magnetic field will point into the page, which is the opposite direction of the change in the flux. And again, if you apply it to the loop of wire growing in size, what would happen? Well, obviously you know that then you would have a current induced that will be running. Okay, if the loop of wire grows in size, then be running in this direction. Because if it grows in size, then there'll be a flux increasing into the page. So this a counterclockwise current will decrease the flux into the page because it will create a flux that's pointing out of the page. If the loop is moved out of the magnetic field, then you can think of this B term as decreasing. So your flux is decreasing, meaning that your change in flux is pointing out of the screen. So there will be a current induced, oops, there'll be a current induced that will create a magnetic field into the page. And that'll happen if this is the direction of the current. Now, what happens if the loop is spun like a disc? Well, in that case, let's just assume that the shape of the wire stays the same and the magnetic field through the wire stays the same. So in that case, the flux is always constant and there's no change in the flux. There's no current that will be induced. So like there will literally be no current induced. So because there's no EMF, because the flux is not changing over time. Yep, counterclockwise. All right, let's do a few quantitative quantitative examples, and then we can wrap it up for today. A square loop of wire with side length 3 meters is in a constant magnetic field of 5 Tesla. If the square doubles its length in 9 seconds, what is the induced EMF in the wire? All right. Okay, so let's draw a picture. This is a square loop, side length 3 meters, and the magnetic field is 5 Tesla. So my B be equal to 5 Tesla, and I'll say it's pointing B equals to 5 Tesla, and it's pointing into the page. So this will be the direction of my magnetic field. Okay, so I want to look at the change in flux over the change in time. So the delta flux. So right now I don't have the specific d flux over dt. I can only do the delta flux over the delta t. Well, okay, what's the delta flux over delta t? Well, I know delta flux, right? Delta flux would be equal, switch to color. Okay, what's delta flux? Well, delta flux would be equal to B times delta A, because right now my magnetic field stays constant. So delta of the A. Well, what's delta A? Everyone knows the area of a square, so it will just be the B, which is times 5, 5, right? And then times the delta A, doubles its length. So originally it was 3 meters long, and now it's 6 meters long. So if you do the change in the area, you'll find 5 times 27, because it's 36 minus 9. That equals the change in flux. Now, change in flux divided by change in time. Also, I have 5 times 27, right? So 135. And divided by change in time, which is 9 seconds, that equals to the EMF. And you'll find it's equal to 15 volts. And remember, it's actually equal to negative, so it'll be negative 15 volts because so it'll be like because it opposes the change in the flux. So, for example, right now I have a magnetic field pointing inwards. If the square area is increasing, then the flux is increasing into the page. So there will be a EMF induced such that the magnetic field, due to the induced current, will be pointing out of the page because the flux is increasing into the page. And that'll look like that'll be happening if the current is moving in this direction. So you use the right hand rule and be pointing out of the page. Okay, let's do the second problem. If a circular loop was with resistance of 5 ohms in the magnetic field constantly increasing at a rate of 20 Tesla per second, how much current be traveling through the wire? Okay, this is my current loop. It's circular, so say it has radius R. Now, resistance 5 ohms, right? Okay, or yeah, 5 ohms constantly increasing at a rate of 20 Tesla per second. I'll call this little r. Okay, well, what is flux, right? Flux would be equal to pi r squared and times b. Now, d flux over dt, right? I know that pi r squared stays the same. It's only the magnetic field that's changing. So just be pi r squared times dB over dt. And I know that's 20 Tesla per second. So it'll be pi r squared times 20. And then that equals to my epsilon or negative epsilon, but like the magnitude of epsilon. Now, okay, we want to find the current through the wire. And so, okay, 20 pi r squared. Well, you might already know this, but we'll learn this later in the course. You know that V over R equals to the I. It's just your Ohm's law. So this divided by the resistance of the wire would equal to your current. That'll be your answer to the second question. Okay, so today we learned about Ampere's law and Faraday's law. We went over the last homework. So please review the recording. If you have any questions, feel free to ask. I know some of you guys are going on spring break or just had spring break, so make sure you relax a bit. But if you missed any classes, please catch up on the recordings. And if you have any questions, just send us an email. And yeah, that's it for today.